Hello friends, welcome to lecture number 10. This is a lecture where I want to discuss about the slew. Slew can have a very important role in the timing analysis because till now maybe we have discussed whatever the lectures in every videos that we are considering that every timing path and timing constant all are with a simple one. So we didn't discuss about how much that every 0 and 1 for the every timing path they are taking for transition time. We are not discussing about the transition time of that input output signal anything. So slew is not underrated things. It's important for to account the variation how much it is capable of. So if I want to say about slew in timing, is what is slew? That slew is simply that is like I write here that how the signal will rise. Signal will rise. It means that suppose any particular timing point in a timing graph, suppose there is a any gate, and that gate have input signal, and that input signal may be are from high to low and maybe the low to high, like any one of the transition can happen. How much time it's taking from going, how much time the signal is taking to going from one state to another state. This is 0 to VDD, or you can say VDD to 0. Okay, how much? Because here it's not possible that my signal will steep. It's not a steep one. It's ideal case, but it will not possible for the digital uh, symmetry square wave. It's not possible. Either I have to take variation 10 to 90% of the transition time, or sometimes I can take 20 to 80% of that voltage variation. So that's why in notes I written same thing, that the real signal will never reach the exactly 0 or VDD instantly. So slew is measured between the specific voltage threshold defined by any standard cell library. Okay, and I think from analog electronics, maybe some of you know that how the slew rate can measure. This is the formula del V by del T with the timing. Why we are discussing about the slew? Slew can affect various part of the designing process in VLSI. That in STA slew is not just affect property of the wire. It can affect the cell delay, cell output slew, setup, hold timing, crosstalk, and signal integrity. Why I am saying that? Because cell delay, it's simple, that buffer, you don't you there is the input output obviously. So if the signal is taking this much amount, very steep, maybe the signal is like that way, maybe the signal is like that way. So that transition time actually matters, how much time it's taking from going from one state to another state. And for that, that slew is added with the cell delay itself has a delay, and that slew have added with that cell delay, and it can affect the output. So output slew can increase, it will not decrease some most of the times, obviously not, because input every input should have some less or maybe big amount of slew, but obviously there will be a slew, obviously there will be a delay. So cell delay, cell output slew, both I think discussed. I so much more increase in the input slew, obviously cell delay also increase, and the output slew also increase. So if you remember this type of two flop in a series, and there is a combinational a cloud, whatever the signal is coming from in the particular combinational path, whatever the small logic gates we may be combination with, when the input is reaching at the every timing input point, because of that slew there will be a delay. And because this combinational data path timing is considered to calculate for the setup time and hold time mostly, so obviously that setup and hold time will affect more the slew, more the delay, obviously that that t arrival time will increase, and if the t arrival time will increase, then there will be a less margin in the total clock path, total clock time period, and there can be a more susceptible to the timing violation of hold and setup. Now coming to the why we have to propagate the slew throughout that combinational path or throughout the sequential path. We have to how to propagate. So for computing the delays for a given stages, obviously I said there is a combinational cloud maybe, and that particular cloud, if this one of the stage, then that delay for that given stage, that slews at its inputs must be known, and STA tool must also propagate the slew in the timing graph, and the propagated slew can be different to the different combinational path. So for that I have taken one example. This is one NAND gate, and if you consider that particular NAND gate, obviously there three input, suppose A, B and C, and every input is equipped with different signal is coming into that path. So that that slew for that every three, for three path is different. Suppose for this one the slew is 8 picosecond, for this one the slew may be 10 picosecond, and for this one the slew may be 16 picosecond. So there can be a various slew is coming at that particular output. How you can consider which slew you should consider. You're confused in that part. So instead of taking every slew to store at that timing point, just take the maximum and minimum one. Okay, so we only storing maximum and minimum slew, and then propagate through that every combinational path or the every data path, you can say, with the help of STA tool. Now coming to that, some notes I written here for you, that what is the relationship between the slew and delay. Maybe in that last 6 to 8 minute discussion I clearly notified those things, but still for you I think, because that why I'm said like this one, monotonically non-decreasing function, because uh, if there is input slew is increasing or transition time is increasing, obviously there will be no chance or no uh, there is no chance to decrease the slew in the output. There will always be an increase, or either it's no change. Another thing that, as I said, like because STA tool can propagate throughout the data path or combinational path, so each timing point should store the maximum and minimum slew uh, it is equipped to it. Okay, and that can be crucial for the timing closure. So these three nodes can help to you to understand. Now coming to that slew propagation expression, how you should express in mathematical term. So this is very important, and I think you'll understand. Let's just define. This is one vertex vi. These all are the input vertex, and these all are the output vertex. Okay, here I will mention ai as a arrival time. Okay, and si AI is arrival time at the input. If AJ, then obviously arrival time at the output. So just think according to that. And SI is a slew time, and OSI is the output slew time. So if that three vertex, in that three vertex, obviously every vertex can store the maximum and minimum arrival time. So I just, for simplicity, I taken here that arrival time maximum and arrival time minimum also with input maximum slew and input minimum slew. Just for simple case, I taken that. Then, because three path may have a different delay from Vi to Vj vertex, so for that you can say I taken that Dij maximum and Dij minimum, and same OSij maximum and OSij minimum. And obviously if we add and something subtract, then I will land up at Aj maximum and Aj minimum with that output slew also. This output slew can have another input slew of another gate. So this is the whole things. If you try to write the formula, then it's simple, like if Aj max is maximum of Ai maximum, that one, Ai maximum, that one, with Dij max. If Aj minimum, then this is the minimum of Ai minimum plus Dij minimum, and also Sj minimum is minimum of output slew Ij minimum, and Sj maximum is maximum of output slew Ij maximum. So I think mathematically you also understand how to express that. Now coming to a example, which by that I think you understand very well. Here this is a path of A, B, C, D, and one path is ACD and one path is a BCD. Okay, and every node I mentioned that A node and B node, I mentioned the maximum arrival time and maximum slew time, and that DBC delay and DAC delay and output slew I also mentioned as a maximum one. And this is the table. This table is mainly for representing the CD connection, and that minimum one and maximum one I tried taken an example from somewhere. So for according to the rule and what are the expression we already expressed here, try to calculate that arrival time at that AC. So AC maximum would be how much? That AC have a two path. One path is at the C point. That arrival time at the C maximum. I have to, because C have a two path, one A to C and another is a B to C. So calculate that maximum one. So 100 plus this is 40. So 40 and 100, and another one is a 20 plus 80. So 20 plus 80. So how much it is? 140 because of maximum one. Okay, and what should be the maximum slew here? Maximum slew, this path have a 10 and this path have a 30. So if I take the maximum, so 10 comma 30, obviously I will get 30. But and as well, when you calculate the slew for D point and arrival time of the D point, 100 because I am taking the maximum one, so obviously I go with this one, this path. So AD maximum is 140 plus 100. So because this is 100, so that's why this is a 240, and slew at the D point maximum is a how much? This is 20. So that's why this is a 20. Okay, but here is a catch, or you can say a contradiction, that I calculate the arrival time at the C point maximally with the help of the path A to C. But if you carefully observe that I calculate the slew for the C point, for the C point I calculate the slew with the help of that B to C point. So I am taking one time A to C for arrival time calculation, and another time I take B to C for slew calculation. So this is a contradiction. But this is not contradiction. It's not as a contradiction, you can say. It's a GBA. GBA, what it is? Graph based analysis. We done the graph based analysis, so that's why it's look like that. Okay, if you go with the path based analysis, which is time taken, then you have to consider every particular path. One path you should consider as a ACD, and another path you should consider as a BCD. Then you have to calculate different two time, C point and D point arrival times slew all. So let's calculate that if you consider ACD path, then at C point the arrival time at the C point, the arrival time is how much? Let's calculate it. As you know, 100, and then there is a 40, so 140, no changes, but D point 140 plus 100, so obviously 240. No, C point, that C point particularly I add this 100 and this 40, so 140, and because I follow this path, so that's why I have to take this 30, then 100 pot 40 plus 30 is D point arrival time will be 170. I think you understand. And slew at the C point is how much? 10, because I taken that slew, this slew, and now I will take the slew of for this 10. So slew at D point is also 10, and if I go with the B, C and D path, then C point, my arrival time would be how much? This 20, this 80, so 100. So this is 100, and D point already I have the 100. I will add with this 100 because last time I had the 30 with that ACD path. Now I'll add the 100 for the BCD path. So now it's coming as a 200. and slew for the C point is how much? This 30, this 30, and slew for the D point will this 20. So now I think understand that what is the difference between the graph based analysis and path based analysis, because graph based analysis is fast, so we are taking the fast path as possible because it will take the it will take the safe bound but not a particular one, not a correct one. But path based analysis is a time taken, and it will calculate the path specific computationally difficulties. I think I hope that you understand that how slew is important for the timing estimation and timing calculation. So thank you for listening patiently. Thank you.